All right, so here is the warm-up for today. Just a quick reminder, I should probably put this in here, that the homework 5 in the textbook, okay, don't do not do. Instead, do the handout or the worksheet. That's up on the front table. Okay, so if you need to grab that, grab that. Okay, so we're just going to do a quick warm-up. The first thing is, what pressure is required to contain 0.023 moles of nitrogen gas in a 4.2 liter container at a temperature of 20 degrees Celsius? Okay, you'll go through and do that one. The next question you'll go through is, what will the new volume of a balloon be when it is 134 milliliters at 30 degrees Celsius and is then heated to 60 degrees Celsius? Keep in mind your units. I will ask the the sub in the room right now to go ahead and pause this video to give you a few minutes to work through this, this warm-up. Once ample time has passed, I would probably give it 10 minutes, probably go ahead and play this again, and I will go through the answers. So I'll give you a moment now to pause. All right, hopefully that was correctly paused. Now we can go through the answers together. Hopefully you're feeling a little bit more confident on this, but if not, that's okay. Follow along. Lots of practice is the key to doing well with these ideal gas law problems. So this first one, what pressure is required? Okay, so we're looking for pressure. So we're going to do pressure equals question mark. Okay, to contain this many moles, so moles is N, so we do 0.023 moles of nitrogen. Honestly, it doesn't matter what type of gas we're working with. Then we're going to go on. All right, we've got 4.2 liters. Liters is a volume, so volume equals 4.2 liters at a temperature of 20 degrees Celsius. We'll be working with the equation PV equals nRT. To get P by itself, we'll divide both sides by V, giving us P equals nRT divided by V. Okay, we need R, so you'll look up back in your notes if you need to, or you have your own equation sheet you can look off of. You're going to look at the ones that matches the pressure. Well, we don't know what pressure we'll be working with here. So in a case like this, I have to accept multiple answers. In this example, I am going to pick atmospheres, but I'll give you the answers to what the other ones should be as well if you decide to go with another one. So liters, atmospheres per mole, Kelvin. Okay, looking at my units, everything matches except degrees Celsius. This needs to be in Kelvin. To do so, you're going to add 273. This brings us to 293 Kelvin. All right, plugging it all in, I have got 0.023 moles times our R, which is 0.0821 liters atmosphere per mole Kelvin, times our temperature, which is 293 Kelvin, all divided by our volume, which is 4.2 liters. I was silly, I forgot to calculate this out ahead of time, so give me 2 seconds to plug this in. All right, this gives me a pressure of 0.1, and then let's see, sig figs, I should have 2 sig figs, so 1.3 atmosphere. Okay, so if you did atmosphere, that would be the correct answer. If you chose, if you chose to use the kilopascal number, that will be, 2 seconds, that will be 13 kilopascal. Or if you chose instead to use the millimeters of mercury, or torr, instead the answer would be 100 millimeters of mercury, or torr is the same thing, 100 torr. Any of those answers are acceptable. Okay, going from here, number 2. What will the new volume? Okay, this indicates to me we're going to have a change. So we need to use that second equation, not just the straight Pubnart, but the conversion 1. Okay, so we're looking for a new volume. That would be a V2. So I'm looking for V2. All right, when it is, so V1, 134 milliliters at T1 is 30 degrees Celsius, and T2 is 60 degrees Celsius. All right, we're going to use our P1V1 over N1T1 equals P2V2 over N2T2. If I don't give you something in the problem statement, such as N, we assume it hasn't changed. So we can say they're equal, and they can then be crossed out. Same goes for the pressure. Okay, so we'll want to rearrange for V2. To do so, we're going to multiply by our T2 on both sides to cancel out, sorry about that, to cancel out our T2 and leave us just with V2. So this gives us an equation of V2 equals T2 V1 over T1. Looking at my volumes and temperatures, are they in units that we should and can be working with? Hopefully you answered no. So we'll take 134 milliliters, set up our dimensional analysis. Milliliters on bottom, liters up top. For every 1 liter, we have 1,000 milliliters. Cancel those out. Our V1 will end up equaling 0.134 liters. T1, you have to add 273 to 30. So that'll be 303 Kelvin. T2, you're going to do 273 plus our 60. So that gives us 333 Kelvin. Now I can start plugging things in. V2 equals 333 Kelvin times our volume, which is 0.134 liters, all over 303 Kelvin. There's a lot of threes here. Oh well. All right, kelvins cancel out. Our units we're left with are liters. When you plug this into your calculator, you end up with 2 seconds, 303, 0.147267, etc. liters. Looking back at our original problem statement, well, volume 1 has 3 sig figs. Volume 2, or temperature 1 has 2 sig figs. Temperature 2 has 2 sig figs, so our final one should have 2 sig figs. 1, 2, looking at that 7, it rounds up. So this will give us 0.15 liters as our final answer. If I wanted to do a direct comparison to that 134 milliliters, I might want to convert that back to milliliters, in which case I would put liters on bottom, milliliters up top. For every 1 liter, I have 1,000 milliliters, canceling out my liters. Okay, so an additional option for this answer would be 150 milliliters. All right, so that's our warm-up. Okay, definitely be doing the homework for this one. At the very least, do that homework that I handed out, that worksheet. Again, it'll be collected just like all the other ones on test day. But the more practice that you do with ideal gas law, the better you'll get at this. This requires a lot of practice, so make sure you're practicing. Today we're going to go into something called partial pressure. This is what you'll need to know for your lab on Monday. Okay, so on Monday we'll be dealing with a lab with partial pressure. All right, so for the lab, we will react zinc with hydrochloric acid, or HCl. All right, this will produce zinc chloride and hydrogen gas. Okay, so if I were to write this in an equation, it'll be zinc as a solid reacting with HCl. Aqueous, remember aqueous means that it's dissolved in water. So these little subscripts with letters in it indicate the state of matter. The first one is solid. The next one is aqueous. It's dissolved in water. It's going to go to zinc chloride, which will be aqueous. It'll be dissolved in that water, and H2 gas. So that's the reaction we are looking at for our lab on Monday. What it'll look like is basically you'll have, now let's see, I probably want to make it further down here. You'll have a beaker with some water in it. You'll get a big long tube with a stopper and a little hole, so that way you can have some more pressure equalization going on. Okay, we'll put a little thing of zinc in here on a piece of string. It'll react with some HCl and water that's in the tube. As time goes on, that zinc will react, and you'll see little bubbles come up and create a nice little pocket of gases up here. This is going to be your H2 gas. Now, there's not just only HCl in this liquid here. It started with HCl, but remember we said it was aqueous, so that means it's in water. So we also have water here. Okay, our goal of the lab is that we will want to find the amount of H2 gas. But some of the gas up here, where the H2 gas is also going to be H2O, water vapor. Okay, so in order to find just H2, we need to look at what's called Dalton's law. So, when we have multiple gases, the total pressure will equal the partial pressures added together. Okay, so if I rewrote that, that would be PT equals P1 plus P2 plus P3, etc. Where if we're looking at PT, that's the total pressure. P1, this is a partial pressure. This is a partial pressure, pressure of substance 1 right? P2 is a partial pressure of substance 2. P3 is a partial pressure of substance 3. Honestly, it doesn't matter how many of these you have. You can add up as many different gases as you have in there to look at partial pressures. In the case of our lab, on Monday, you'll see that we just have H2 and H2O. They'll just be 2. Okay, this is called Dalton's law. Okay, so looking at this, if you collect 185 milliliters of gas, so this is looking at the lab example, okay? So let's just say we had 185 milliliters of gas total, which is, so it is both H2O vapor and, excuse me, H2 gas. Okay, to find just the pressure of H2 gas, we'll use Dalton's law. You need to use Dalton's law. Okay. So specifically, if the total pressure is 0.946 atmosphere. And I'll show you in the lab how we'll be getting that total pressure. And then we'll take the room temperature. Just for the sake of this example, we're going to say the room's a heck of a lot warmer, and we'll say it's 27 degrees Celsius. Okay, what is the partial pressure of H2 and how many moles of H2 are present when the vapor pressure of water is 32 millimeters of mercury at 27 degrees Celsius. Okay. So this is kind of an example of something you might look at. So the first thing that's asked is trying to find the partial pressure of H2. So using Dalton's law, which we just got, we're going to have P total is going to be equal the partial pressure of H2 plus the partial pressure of H2O, because we know that both of those are present in the tube. And because water, it has a pretty strong IMF, but it's not quite strong enough to not have any water vapor in the gas phase. So there will be some water vapor molecules up there. Okay, so we'll just specify that it's vapor. Okay, well, looking at this, the total pressure. So I give you the total pressure. So we know that that is 0.946 atmospheres. We're trying to find pH2, so obviously we do not know that. But the vapor pressure is something that you can look up. This has a vapor pressure of 32 millimeters of mercury. So, 32 millimeters of mercury. If I were to solve this, do you think I can continue solving this if these two units are different? Hopefully you're answering to yourself, heck no. Now it doesn't matter which way I convert this. I can convert everything over to atmospheres. I can convert everything over to millimeters of mercury. Regardless of the way you decide to go about this, you should end up getting the same answer. So I'm going to pick atmospheres because I like atmospheres. We'll start with that one. So let's take our 32 millimeters of mercury and let's convert it to atmospheres. I'll set up my dimensional analysis. I want millimeters of mercury on the bottom. I want to go to atmospheres. Okay, looking back at the notes we've done the last couple days, for every 1 atmosphere you have 760 millimeters of mercury. Again, that is going to be on that equation sheet for you, not something you'll have to memorize. Millimeters of mercury cancel out, and this gives me 0.0421 atmospheres. Now my units are matching up. Now I can go through and solve this. So I've got 0.946 atmospheres, our total, equals our pH2 plus 0.0421 atmospheres. If you solve for pH2, we end up with 0.904 atmospheres. Oops, somehow I missed the T. All right, that's our first question, was just what is the partial pressure of H2? There you go. We've solved for that. Now the next question that's asked is how many moles of H2 are present? Well, we're given a heck of a lot of information here. We have a pressure that we can use. Do you think we can figure out the moles of H2? We sure can. We can use the ideal gas law to get the moles of H2. So we can use PV equals nRT and solve for moles. So if I rearrange this equation to solve for moles, I'm going to divide by RT on both sides. This gives me N equals PV over RT. Well, what variables do we have? Well, we're working with, we just want the moles of H2. So we want the partial pressure of H2. So our pressure here is going to be that 0.904 atmospheres because we're just interested in the hydrogen gas. The volume. Let's take a look at volume. Let's look back up at our problem. See if it gives us volume. It sure does. So up here you can see 185 milliliters. Now you might be thinking, wait, but that's like the whole space up there and it's being shared. Well, both the water vapor and the H2 is taking up all of that space. They're mixed homogeneously. And so when you look at volume, they both occupy the same amount of volume. So it's still going to be 185 milliliters. We don't need to adjust that. So that's 185 milliliters. Okay, the next bit of information that we have is T, which is 27 degrees Celsius. As we look back up here, there we go, 27 degrees Celsius. All right, we'll need R, so we want to put an R that matches our pressures units. So we'll want to use 0.0821 liters atmosphere per mole Kelvin. Remember, we want to match up all our units. So atmospheres matches, hooray! Does milliliters match liters? Heck no. So we got to do a quick conversion. So we want milliliters on bottom, liters up top. For every 1 liter, we have 1,000 milliliters. This gives us 0.185 liters. Celsius needs to be converted over to Kelvin, so we add 273. This gives us 300 Kelvin. Now I can plug in for the number of moles. NH2 is going to be equal to 0.904 atmospheres, the partial pressure of the H2, times our 0.185 liters, all divided by our R, 0.0821 liters atmosphere per mole Kelvin, times our 300 Kelvin. Again, check your units. So if I have something up top and something on bottom, they'll cancel. So I have an atmospheres up top, atmospheres on bottom. Liters up top, liters on bottom, and a Kelvin up top and a Kelvin on bottom. We're left with moles, which is what we want. Plugging this into my calculator, I end up with 0.00679 moles of H2 gas. Let's see if that's correct sig figs. Let's see. Oh, I don't need to go up that far. Here we go. This one is 3 sig figs. This next one is also 3 sig figs. This one's 3 sig figs, and we don't use R in our decision for sig figs. So this one is also 3 sig figs. So this would be our final answer. Okie dokie. So that's the idea of partial pressure. It's basically just saying that a total pressure is going to be equal to all of the gases' pressures added together. So what you'll be doing with the rest of this period is, first of all, you can go through, double check your answers, and work with one another on that speed friending activity. Okay, I have the answers posted on Schoology, and there's also a key up front. Feel free to check yourselves and work through this. Make sure that you're feeling comfortable on this, because this is going to be very important to understand each aspect of this. Once you finish that, okay, so we're going to do 2 things here. So today, you're going to do 2 things here. The first one is that you are going to check your ideal gas law speed friending answers. And if you didn't finish through it, this is a good time to finish through that. When you're done doing that, you are going to work on lab 16, which is on page 79 in your purple lab manual. Okay, for this lab, this one is going to be a full lab write-up. I'm not going to do too many throughout the year. They've decided this year, but this one is one I want you to do. Full lab write-up. Which means it's going to be in your lab notebooks. Okay, those lab notebooks are found in the boxes in the back. So feel free to go grab your lab notebook as soon as I'm done talking here, so that way you've got it and you're ready to go. In order for this to be a full lab write-up, you will include the lab title, the pre-lab answers. You don't need to put the questions in, you just need to put the answers in, followed by the purpose. Remember, the purpose is only 1 sentence, your own words. So simplified quite a bit. Okay, the safety and procedure. Remember, for the procedure, this is just a shortened version. And again, it's in your own words. The last thing you need is you'll have to read through the procedure to understand what you'll be collecting, and you need to have a data table ready to go for collecting data on Monday. That way you're not trying to scramble to put together a data table while we're collecting the data. Okay, so those are the, let's see, 1, 2, 3, 4, 5, 6 things. Really, lab title, I'm not sure I fully count that. 5 things within the lab that need to be done come Monday. All right, again, sorry I'm not there. If you have questions, feel free to email me. You got the rest of the class period. You may work in your groups. Again, finish up your ideal gas law speed friending. Make sure that you check those answers with the key up front and work with one another on that. When you're done with that, you may use the time to work on lab 16, which is dealing with Dalton's law. You'll go through and do a full lab write-up for this one, so make sure you have all your pre-lab stuff done. That includes pre-lab answers, purpose, safety, procedure, and data tables. I will be back on Monday, hopefully, and we will do the lab on Monday.